session, I am going to talk about the concept of resonance and molecular orbital theory. Let me move with the concept of resonance. As we know, electronic structure of molecules or ions can be represented in the form of Lewis dot structure. But remember that using one Lewis dot structure, we cannot explain all the properties of molecules or ions. Therefore, the molecule or ion what we represent in the form of Lewis structure can be represented in another form also, and that we consider it as contributing structures, where the position of atoms will be same but the electronic structure is going to differ. So the description of electronic structure of molecules or ions by different contributing structures is termed as resonance. And the different contributing structures what we get, and if you consider the average of these contributing structures, is termed as the resonance hybrid. So this is the meaning of resonance and resonance hybrid. We'll consider one very simple example and we'll try to understand what actually resonance and how we can draw the structure of resonance hybrid also. I will consider the structure of a benzene proposed by K. Cooley. So as we know, the molecular formula of benzene is C6H6, and this is the structure of a benzene. We have three alternative double bonds. So this is the one contributing structure or canonical structure I can write here. So now what happens in resonance, the main concept is there will be shift of electrons. Remember that in a benzene, if you consider this example, in benzene ring, the electrons, especially the pi electrons, are not localized, they are not static. They used to revolve in the benzene ring, and that we termed it as delocalization. So resonance is nothing but, in simple language I can say, there will be delocalization of electron, there will be shift of electrons I can say. So what happens, this is the pi electron, this is going to shift over here, and this pi electron is going to shift over here, and this pi electron is going to shift over here. So we will get one more structure of the identical type, and this is how I can draw the structure of that. But here this pi electrons is going to shift over here, therefore we will get a double bond over here, similarly double bond over here, and similarly one more double bond over here you are going to get. So this is also benzene and this is also benzene. But what is the change we are going to observe in these two? The position of electron is different. So what happened actually, there will be a shift of electrons takes place, so that one more structure we are going to get, and that is termed as contributing structure or canonical structure we are going to write here. So now after this we'll write the resonance hybrid. So for benzene we have these two canonical structures. So resonance can be represented in this fashion, the arrow mark, double-headed arrow mark like this in the left side as well as the right side, and resonance hybrid we are supposed to indicate like this. So how to represent the resonance hybrid is, so this is the benzene ring what we have. In a resonance hybrid, the main part is the electron is going to delocalize, as we know. So the path which is shifted by electrons, we have to represent that. So here we have a alternative double bond over here and over here. In this case here, here and here we have. In general I can say the pi electron is going to rotate inside the benzene ring. So this is how we can show that, and using dotted lines I can show here. That indicates that the pi electrons are going to rotate in this fashion in the benzene ring, but they are not localized, they are delocalized I can say. So therefore these two structures what I represented, and these two I can call it as contributing structures. These two I can call it as contributing structures, or I can call it as canonical structures, and in general we call it as resonance structures. So this is how resonance structures can be represented, whereas this, the diagram what I represented, and this is termed as resonance hybrid. This is resonance hybrid. So this is how we can represent the electronic structure of a molecule or ion by different contributing structures is called resonance, and the average of contributing structures can be represented by a description representation, and that is considered to be resonance hybrid. Remember that resonance hybrid is quite stable when compared to respective contributing structures, and that is the concept of resonance and resonance hybrid. Now we'll see how to write the resonating structures of different molecules, and before moving with that, we'll see what are the rules to be followed, or I can say what are the conditions to be applied while writing the resonating structures of molecules or ions. The first point or the first rule, what I can say here, same atomic position, you need to write the contributing structures in such a way that the position of atoms should be same. If you consider the same example, we have a carbon over there and hydrogen over there, the position of carbon and hydrogen is fixed. So remember that in resonating structures, the position of atoms should be same, they are not supposed to change. Whereas the second one I am going to write, different electronic position, atomic position should be same, whereas the position of electrons should be different. So here we have a pi electrons in this contributing structure, and when you compare the one more contributing structure, the position of electron is not same, they are different actually. So in a contributing structure, the position of electron should be different. Next, same number of unpaired electrons. The one more condition is the number of unpaired electrons in a different contributing structure should be same. If you consider a compound or a molecule or ion with a nitrogen, it has one lone pair of electrons. If you consider oxygen, it has two lone pair of electrons, and that has to validate the valence electrons of respective element. In short, I can say the number of unpaired electrons should be same. The next condition, almost same energy. As I told you, the different contributing structures, they are going to differ in energy, that too with a very small extent. The contributing structure should possess energy, should not differ with greater in magnitude, or I can say they should have almost the same energy. Of course, the energy of resonating hybrid will be quite lesser, because of that is quite stable when compared to contributing structures. Next one, negative charge should reside over electronegative element, whereas the positive charge should reside over electropositive element. So this concept you try to know. So the negative charge, if you consider the example of ions, and when there is a shift of electrons, of course sometimes we get negative charge, sometimes we get a positive charge. Negative charge should reside over the element which is electronegative in nature. Similarly, positive charge should reside over element with more electropositive element, since there will be mutual sharing of electrons. As we know, if an element is more electronegative in nature, and what I am going to say here is that particular element which is more electronegative, that attracts the shared pair of electrons towards itself, because of that you will get a partial negative charge over there. If it is less electronegative or more electropositive, you can say that gets partial positive charge. So based on that I can say, if you have a negative charge, that should reside over electronegative element, a positive charge should reside over electropositive element. By following this rule, we need to draw the canonical structure or resonating structures of a molecule or ion. If you have the like charges, and if the atoms, two different atoms, if it has a like charges, positive or negative, that should not be close, that should be far away from each other. Whereas if it has unlike charges, one is positive and one is negative, that should be almost as close as possible. As we know, like charges repel each other. So if you consider the two positively charged atoms, and what happens, there will be a repulsion and the stability of molecule will be not good, isn't it? So if you have atoms with the like charges, they should be far as possible. Whereas if oppositely charged, if you consider plus and minus, and opposite charge, they attract each other, that contributes to stability, therefore that should be as close as possible. So all these are the conditions you need to remember to draw the resonating structures of molecule or ions. Remember that the atomic position should be same, electronic position should be different, number of unpaired electrons should be same, and they should have almost same energy, and the negative charge should be present on electronegative element and positive charge should be present on electropositive element. And if there is a chance of like ions and unlike ions, that depends on how the stability of molecule can be explained. So all these are the rules or conditions to write the resonating structures. So now, after knowing the rules, and we'll write some examples how we can draw the resonating structures of molecules. So let me consider the first example, that is carbonate ion, that is CO3 2-, carbonate ion. So we'll write the structure of carbonate ion, and we will apply the concept of resonating structures, and we'll follow the rules of resonating structures, and we'll see how many resonating structures are possible for carbonate ion. So CO3 2- we have here. So we'll see how we can draw the structure of CO3 2-. So now you just see here carbon we have, and here I am going to write a double bond oxygen, and single bond oxygen and single bond oxygen, and here I will write a minus, and here I will write a minus. Remember that Lewis dot representation represents the number of valence electron. Similarly, while drawing the structure of resonating structures, you should know the concept of a valence electron and the valence electron of the elements or atoms involved in the particular molecule. So we have CO3 2-, the valence electron in carbon is 4, and the valency of oxygen will be 6. So now here we can represent the valence electron using dots, that we call it as Lewis dot representation, and the valency of oxygen will be 6. So 6 dots we have to represent, and out of that we have a bonded pair of electrons also. So for this oxygen we have 1, 2, 3, 4. 4 electrons I am going to consider, 1, 2, 3, 4, and the remaining 2 electrons are involved in bonding with the carbon. So now similarly for this carbon we have a 4 valence electron, 1, 2, 3, 4. It is mutually shared with 3 different oxygen, that is okay for that one. Then for this oxygen, oxygen has 6 valent electron, minus represent it has extra electron, excess electron. So here I am supposed to represent 3 pairs of electrons. Okay, so 1, 2, 3, 4, 5, 6 we have, 1, 2, 3, 4, 5, 6, 7 we have, therefore we write a minus over here. So for this also I need to consider the 3 pairs of dots, and that is how this is the Lewis dot representation of carbonate. So now we'll see what would be the resonating structures. As we know, resonating structures can be represented in this fashion. So in simple, I explained the resonating structure is nothing but the shift of electrons, delocalization of electrons. So what happens here? For this oxygen we have extra electron, for this oxygen this is electron rich, I can say. So this minus electron is going to shift over here, and this pi electron of carbon oxygen is going to shift over here. This is how the shift of electrons takes place. And after shifting, so what kind of structures we get? So now see, so we have a pi bond, pi electrons is going to shift over here. So therefore O I write here, we get a minus over there since pi electron has been shifted. So we have O minus as it is unchanged. Here the minus, the extra electron has been shifted over here. Therefore here we get carbon double bond oxygen. And similarly we can represent the Lewis dots. Okay, so for this oxygen we need to draw the 2 pairs or 4 electrons here, 1, 2, 3, 4, 5, 6 electrons, and 1, 2, 3, 4, 5, 6 around the particular atom we need to mention here. So this is how the contributing structure of carbonate I can represent like this. So one more contributing structure I can represent here. So observe here how I am going to represent that. So 1 electron has been shifted over here. So in this structure I am going to shift the electron over here, and this is how the pi electron is going to shift over here. And this kind of after shifting the structure I am going to write, so O minus as it is. So here you get a carbon double bond oxygen, and here you get a carbon single bond oxygen. So minus a sign we are going to get, and we will represent with the dots. Here we have 2 pairs, and for this oxygen we have 3 pairs. And for this oxygen also we have a 3 pairs. So dots represents the number of valence electron, and using that concept we can draw the resonating structures of carbonate like this. So if you observe these 3 different contributing structures, we came to know that the position of atom is same, but whereas the position of electron is going to be differ, and which is more electronegative, that has a negative charge, so minus charge we are going to calculate here. And you need to remember the valence electron, and based on that we can write the resonating structures like this. Second example I am going to consider, and the second example is about NO3 minus. So NO3 minus, nitrate ion this is. So we'll see how we can write the contributing structures for nitrate ion. Nitrogen we have, so 3 oxygen we have, isn't it? So double bond O here, and double bond O I can represent here, and a single bond O, and for this oxygen gets a minus charge because we have only one minus on one oxygen. This is how I can represent the Lewis dot representation. And as we know, oxygen, the valency will be 6. Okay, so 2 are involved here, so therefore 2 pair of electrons I need to represent, and here also 2 lone pair of electrons, and for this one we need to represent the 3 pairs of electrons. So that is the Lewis dot representation for nitrate, and we'll see the contributing structures for this. So resonating structure for this particular nitrate. So we have electron excess, so this will shift over here, and we can consider shift of electrons over in this fashion. So what we are going to get, so here you get nitrogen O minus I am going to consider. So double bond O will be as it is. So here there will be a shift of electrons. So double bond O we are going to consider. So here also we have one O minus, and in this structure also we have one O minus. Will represent the Lewis dots. That depends on the valence electrons. And now we can draw one more ionic structure for that one. So one more resonating structure. So in this case what happens, this electron will come over here, and this pi electron will come over here, and because of that what kind of resonating structure we get? Nitrogen double bond oxygen we get, and here there will be a shift of pi electrons, I can say O minus we are going to get, and here we have double bond O over here, and we'll write the Lewis dots as it is, as I mentioned. And this is how the different contributing structures or resonating structures for nitrate can be written. One more example, that is about ozone, O3. So these two are the ions, and now I am going to talk about ozone. So how the Lewis dot representation and resonating structures can be represented for ozone. As we know, this is the structure of ozone. Okay, so 3 oxygens we have, and in between one we have a double bond, and here we have a single bond, and the valency of oxygen will be 6. Okay, and usually it forms a double bond, so we have 3 bonded pairs, therefore 1 extra we have, and we have 1 excess, so therefore minus I am going to consider here. So now if you consider the Lewis dot representation of this, and now we'll see what would be the resonating structures we can draw over here. So we can draw the Lewis dots. So 2 pairs we have, and here we have 3 pairs to balance that, and of course for this one also we have 1 pair of electrons. So what happens here? So there will be a shift of electrons like this, and this oxygen will be in this fashion. So what we get? We get oxygen over here. So the pi electron has been shifted, therefore O minus we are going to get, and here we get a double bond O, and here we get a plus sign as it is, and we have a minus sign over here. We'll represent the Lewis dots for here, and of course we get the depending upon the number of valence electron. So in this case of ozone, only 2 canonical structures or contributing structures are possible. So if you consider the same thing again, if you shift the pi electrons over, and if you shift pi electrons over here, you are going to get the same canonical structure. So this is how we can represent the molecule or ion in the form of different resonating structures. We'll see the resonating structures of carbon dioxide and carbon monoxide. The fourth example I am going to consider, that is carbon dioxide. As we know, carbon dioxide is a linear molecule, since the dipole moment of carbon dioxide is 0. So this is the structure of carbon dioxide, and as we know, oxygen has 2 lone pair of electrons over here and 2 lone pair of electrons over here. So now we'll see what would be the resonating structure of carbon dioxide. So we have a pair of electrons, so that will shift over here, and the valency of carbon will be 4. Because of that, the pi electron will be shift over in this fashion. So how I am going to represent that? So carbon we have here, so pi electron has been shifted here, therefore 3 bonds we are going to get, and oxygen we have. So pi electron shifted in this fashion, so we have a single bond and we have oxygen. So pi electron has been given, therefore it gets a positive charge, and it has been gained, this gets a negative charge over here. And the electrons, you need to remember for that how many electrons we get, and here we get 3, 4, 5, and 1 extra we have, 1 as given. And now this is how the carbon dioxide canonical structures can be written. So one more structure, canonic structure of carbon dioxide, we can write over here, and that I am going to write here. So observe here, so there will be a shift of these lone pair of electrons over here and pi electrons over here. So let us assume will be shift of electrons in this fashion, and the pi electrons will shift over here. So in that fashion, what we are going to get? So pi electrons will shift here, because of that reason we will get 3 bonds over here, and here we get a single bond and oxygen, and the sign will be, for this you will get plus, and for this you will get a minus, and the Lewis dots you need to represent as it is what I mentioned. So carbon dioxide has these kind of resonating structures, which is linear. We'll see the next one, that is about the carbon monoxide. So what would be the resonating structures of carbon monoxide? As we know, the Lewis dot representation for carbon monoxide is like this. So carbon, the valency will be 4, okay, and we have a 3 and 4, 5, therefore it gets a minus charge, and oxygen will be plus charge we are going to get. So resonating structures, so what happens, oxygen is more electronegative, so therefore pi electrons is going to shift in this manner. So what we get, C double bond O we get, because pi electron has been shifted here, and now we have a pair of electrons over here, carbon valence is satisfied, which is 4, and we have a 2 over here, and we will get 2 more. So this is how 1, 2, 3, 4, 5, 6 valence of carbon, oxygen is also verified. So now we'll see one more resonating structure. So we have a pi electron over here, and that is going to shift in this fashion. So I am going to write over here the structure of that. So we get carbon, single bond and oxygen. So 2 electrons we have already over here. So 1, 2, 3, 4, 5, 6 we get here, and here we get plus charge, and here we get minus charge I am going to consider. So 1, 2, 3, 4, 5, 6, 7 we have, 1 extra, therefore minus you need to consider, 1, 2, 3 we have, and 1 scarcity of the electron, therefore plus I am going to consider. So this is how the canonical structure of carbon monoxide can be represented. So this is how, using one Lewis dot representation, of course we cannot explain all the properties of molecules or ions, therefore we are supposed to write the different contributing structures, different canonical structures or different resonating structures, as I mentioned, some of ions as well as molecules. I mentioned that these contributing structures can be represented in a single diagram or single pictorial representation, and that is considered as the resonance hybrid. And in the resonance hybrid, we need to mention in the dotted fashion how does the path of electrons travels. So that I explained with one example. So now we can draw the resonance hybrid for the all, but let me explain only one example for that one. So now I consider the first example, carbonate ion, how we can draw the resonating hybrid for that one. As you know, in this particular example, so here there will be a shift of electrons in this fashion also. So here we have a carbon double bond oxygen, in this particular example carbon double bond oxygen, in this particular structure carbon double bond oxygen. So this is how the 3 paths we have where the electron is going to shift. So carbon we have, so this is how oxygen it is going to be linked with. So that I mentioned that using dots we need to represent. So this is how actually there will be the resonance hybrid I can say, and the charge will be 2 minus, okay, and for that one you need to consider the box, and above we need to write 2 minus, and that is the resonance hybrid of what actually CO3 2 minus. Similarly, in case of NO3 we need to represent the dots. So similarly, where actually there will be a shift of electrons takes place, and that is considered to be the dotted lines, that represents the resonance hybrid. And in resonance hybrid we cannot mention the particular ion you can write, but in general we represent as a whole molecule and what would be the charge of that. So this is how resonating structure helps us to explain some properties. So one example I am going to consider over here. So CH3 C double bond O single bond O minus. So this is as good as CH3COO minus CH3COOH acetic acid or ethanoic acid, CH3COO minus acetate ion it is. So in this molecule also there will be the resonating structures that can be possible, and how we can write that. So try to know we have a minus sign over here, and it is not compulsory to represent the Lewis dots for the all molecules. For your representation I mentioned. So this O minus we have, so means we have extra electrons over this oxygen, so this is going to shift over here, isn't it? And now we have pi electrons to satisfy the valency of carbon, this is going to shift in this fashion. So because of that what we are going to get, so let me write the structure over here. CH through C double bond O we get, and here we get to O minus we get. So this is how we can write the resonating structures for that one. This is represented in this fashion. And if you want to write the resonating hybrid for this one, so how I can represent the hybrid resonance for this one? So carbon we have, and methyl group CH3, and here we have O, and here we have O. So there will be a shift of electrons in this fashion, isn't it? So here I can represent like this. So this is how the path of electron shift can be represented using dottage, okay, and that is considered to be what actually the resonance hybrid. And of course we can mention the charge minus over here. So this is how in case of inorganic molecules also we can represent resonating structures. In case of organic molecules also we can represent the resonating structures, and this will help to write many chemical reactions in chemistry by knowing the concept of resonance. Molecular orbital theory. Many properties of molecules as well as ions can be explained with the help of molecular orbital theory. First we'll see what are the assumptions or postulates of the theory MOT. We know that there will be overlapping of atomic orbitals. When atomic orbitals overlap, then we get molecular orbitals. Remember that when two atomic orbitals overlap, and there will be a particular region where the probability of finding the electron will be more, and the region where the probability of finding the electron will be more, or I can say that is rich in electron density, and that region is considered as molecular orbital. So one very simple example I considered, I am going to talk about the S atomic orbital. As we know that one, the shape will be spherical in shape, and this is one S atomic orbital, and this is the center of the nucleus you can consider, and this is the one more S atomic orbital, okay, and when these two overlap, so what we are going to get, so this is how the overlapping of atomic orbitals takes place, okay, and this is the region of overlapping, and after this we get a molecular orbital I am going to represent here, and one type I am going to consider. This is the molecular orbital which is formed from that. This is the center of these two, just imagine, and here there is a region, or I can say there is a region where the probability of finding the electron will be more, and that is termed as molecular orbitals. So know that these two are the very important to form the molecular orbital. So molecular orbital is nothing but the area in between the two nuclei. So this is the one nuclei and this is the one nuclei. If you consider two nuclei with one electron each, and the area between the two nuclei where the electrons are most probably found. As we know, electrons are not static. So this is a region or the area in between the two nuclei where the chances of finding the electron will be more, and that particular region is termed as the molecular orbital. Then how molecular orbital is formed? As I mentioned, when there is overlapping or the combining of atomic orbitals, then only we are going to get molecular orbitals. Atomic orbitals combine to form molecular orbitals. When atomic orbitals combine, and there will be a formation of molecular orbital, I said there will be a formation of two molecular orbitals, and one we call it as bonding molecular orbital, and the one more we call it as anti-bonding molecular orbital, BMO and ABMO. BMO bonding molecular orbital, ABMO anti-bonding molecular orbital. If you compare the energies of BMO and ABMO, they are not same. Remember that BMO and ABMO are the two types of molecular orbitals which are formed by the combination of atomic orbitals. So BMO is quite stable when compared to ABMO, and because of that reason I can say the energy of BMO is low and it is stable, whereas the energy of ABMO is high and it is unstable. Later we'll see why it is like that. And remember that the molecular orbital which is formed, it has a particular shape, and the shape of the molecular orbital depends on the shape of combining atomic orbitals. So if S atomic orbital is going to be combined and we are going to get a molecular orbital of a spherical shape only. If P atomic orbital will combine, and we know that when P atomic orbital the shape will be dumbbell, and later in the molecular orbital also we are going to get a dumbbell shaped molecular orbital only. That's why I told you that the shape of a molecular orbital depends on the shape of the atomic orbitals. And now you remember, all kind of atomic orbitals, they won't combine as it is. We have particular condition for that. The atomic orbitals should have the same energy, almost identical energy, and they should have almost identical symmetry over there. And if there is same energy as well as same symmetry, then such atomic orbitals will combine. We are going to get molecular orbitals. Only those atomic orbitals of same energy and same symmetry can combine. Same symmetry. Number of unpaired electrons can be used for explaining the concept of a symmetry, or in which direction the lobes of P atomic orbital or S or D we have, based on that also we can say the symmetry of that. If the symmetry is same and the energy is same, then only there will be a formation of molecular orbital. We will see one particular example for that. If I consider 1s, as we know, this 1 is nothing but the principal quantum number and S is nothing but the azimuthal quantum number. 1 is main shell and the second one is subshell. So 1s can only combined with the 1s atomic orbital only. Why? 1 and 1 principal quantum number is same as well as azimuthal quantum number is same. So S and S both are spherical in shape only. The energy is same and symmetry is also same. So if energy is same, symmetry is same, then there will be a chances of combination of these atomic orbitals. Therefore 1s can combine with the 1s atomic orbital only to form molecular orbital. One more example I consider 2px. As we know, for P we have 3 atomic orbitals, px, py, pz, based on in which direction we represent the lobes. So 2px is going to combine with the 2px only. So we have a principal quantum number 2 and azimuthal quantum number p, that is combined with the 2px only. Then we get what actually the molecular orbitals. So if you consider the 1s atomic orbital and if you consider 2s atomic orbital, so 1s and 2s, and if you try to combine these two atomic orbitals, there will be no formation of molecular orbitals. What would be the reason for that? See here, of course the azimuthal quantum number is same, that is yes, spherical in shape. What about the principal quantum number? 1s, 1 it is, and here it is 2. As we know, the energy of 1s is less when compared to 2s. So 1s and 2s are the atomic orbitals of different energy, not the same energy, and if there is a different energy, there will be no combination of such atomic orbitals to get molecular orbitals. Therefore this is not possible. So if you consider 2px with 3px, of course px we have same, but principal quantum number is 2 and principal quantum number is 3, so different energy we have. Even though the shape is same, therefore such kind of combination of atomic orbital is also not possible. This point is very important. Remember that only those atomic orbitals which have same energy and same symmetry, they can only combine to get what actually the molecular orbitals. And now this formation of molecular orbitals, that follows some standard rules. And what are these rules? The filling up of electrons into the molecular orbitals. As we know that if you consider a molecular orbital, there will be occupying of only 2 electrons of the opposite spin. So if you consider this is a molecular orbital and 2 electrons if you have, and this is 1 electron and this is 1 electron, this is plus 1 by 2 and this is minus 1 by 2, that is actually the principal quantum number, and they should be in the opposite direction and only 2 electrons can be filled. And all this concept will depends on some standard rules, as I said, and the first one is Aufbau principle, and the second one is Pauli's exclusion principle, and the third one is Hund's rule. Aufbau principle: filling of electrons into different atomic orbitals takes place in the increasing order of the energy. So as we know, we have different atomic orbitals, s, p, d, f in general if you consider, and the energy will be in the increasing manner. So electron is going to fill in the atomic orbitals in the increasing order of energy. So if you consider 1s and 2s as the atomic orbitals, and the electron is going to fill in the 1s atomic orbital, and later if you have electrons and that is going to fill in the 2s atomic orbital, since the energy is going to be in the increasing manner, and that rule is corresponds to Aufbau principle. Pauli's exclusion principle, as I said, in one molecular orbital there will be 2 electrons of opposite spin. Only electrons of opposite spin can be paired, or you can say no 2 electrons can have same set of 4 quantum numbers. That corresponds to Pauli's exclusion principle. As I said, we need to write only 2 electrons of opposite spin, and that is termed as the Pauli's exclusion principle. One more rule has to be followed, that is Hund's rule. Pairing of electrons starts only after all the atomic orbitals are filled with 1 electron each. So if you consider the atomic orbitals of same energy, this is a very important criteria. If you consider p atomic orbitals and if you consider d atomic orbitals, p and d are of different energy. So in case of Hund's rule, you need to consider atomic orbitals of same energy. So set of p atomic orbitals or set of d atomic orbitals if you consider, and here what happens, the electron starts filling. Of course, first you need to fill all the atomic orbitals with 1 electron each. After that, the pairing of electrons will start, and that is termed as Hund's rule. Remember that in case of a molecular orbital theory, you need to follow Aufbau principle, and you need to follow Hund's rule, and you need to follow Pauli's exclusion principle also. In some cases, if we have the atomic number greater or large atomic number elements, and you need to follow one more rule, and that is termed as extra stability rule. What it says, half filled atomic orbitals and completely filled atomic orbitals are highly stable because they are symmetry in nature. So if you have such electronic configuration which is half filled and completely filled, that is quite a symmetry and that is quite stable. So all these rules has to be followed by filling the electrons in a molecular orbital. That is all about the postulates of MOT, that is nothing but molecular orbital theory. Now we'll see how 2 different molecular orbitals are formed, BMO and ABMO, using a theory called LCAO concept, linear combination of atomic orbitals. Let me consider 2 atoms A and B, and the wave function of A is represented by psi A. So let me write here, let psi A will be the wave function of atom A, and psi B will be the wave function of atom B. So if I consider psi A and psi B will be the wave function of atom A and B, the wave function of a molecular orbital can be represented by linear combination of these atomic orbitals. So how we can represent that wave function of molecular orbitals? So here I am going to consider, so wave function of AB molecular orbital, which is equals to linear combination of atomic orbitals Ca psi A plus I am going to consider Cb and psi B, and we know that one psi A and psi B will be the wave function of A and B, whereas here I represented 2 constants, you can say Ca and Cb, and these I call it as mixing coefficients. These I consider it as mixing coefficients. That depends on what kind of atomic orbitals you consider, whether you consider the same atoms or different atoms, homonuclear atoms or heteronuclear atoms you can consider. So this is how we can represent the wave function of a molecular orbital by considering linear combination of atomic orbitals psi A and psi B. As I mentioned, the molecular orbital should be quite stable when compared to atomic orbital, so that the energy of psi AB or the molecular orbital should have low energy. So because of that, we need to consider the value of Ca and Cb in such a way that the energy of psi AB should be low. So if you consider the A and B are the homonuclear atoms, or you can say the same kind of atoms you can consider. So from that I can write the relation, that is Ca square is equal to Cb square, and this is for homonuclear atoms if you consider A and B. And now I can consider that Ca is equals to plus or minus Cb. If you take the square root of that, Ca is equals to plus or minus Cb, and as I mentioned, these two are actually the mixing coefficients. So based on this I can say there will be a formation of two molecular orbitals with one plus sign and with one minus sign. So the first molecular orbital what we are going to get is psi superscript b. I am going to write here. So superscript b, which is equals to, and here I consider psi a and psi b, and that is nothing but the addition of the atomic orbitals. So addition I consider, so psi b is equals to psi a plus psi b, and one more I am going to consider, that is psi superscript star I am going to write here, and that is equals to psi a minus psi b. So this is how I can represent the two different molecular orbitals. One is psi b and one more is psi a, and we came to know that the atomic orbitals in one case that is going to add, and in one more case that is going to subtract by considering the intermixing of the mixing coefficient you can consider. So this psi b is nothing but a BMO, bonding molecular orbital, whereas psi star is nothing but ABMO, anti-bonding molecular orbital, as I represented that when atomic orbitals of same energy and same symmetry will combine, we get two types of molecular orbital. One is BMO and one is ABMO. BMO is represented in this fashion in the form of wave function, and ABMO can be represented in this fashion in the form of wave function, I can say. And one more concept I told, the energy of BMO and ABMO, and we'll see how actually the energy of BMO and ABMO can be represented. And for that, here I am going to consider the diagram for that. This is how the energy of BMO and ABMO can be represented. So this is how I can consider the different energy levels. Let me draw the diagram first, and we'll see later how actually the atomic orbitals will combine and we get the molecular orbitals. So here this is the energy level diagram you can consider for the BMO and ABMO, and remember the energy will be increasing in this fashion. So this is how the energy is going to be increased. As we know, molecular orbital is formed by combination of atomic orbitals. So as I mentioned, A and B are the two atoms. So psi a, this is the wave function of atom A, and here I consider psi b, and this is a wave function of atom B I am going to consider, and this is the atomic orbital I am going to represent here, AO, atomic orbital, and this is also atomic orbital AO I am going to write. So when atomic orbitals combine, we get the molecular orbitals, that too two different type of molecular orbitals. One is by taking the addition of a wave function, one is by taking the subtraction of a wave functions, actually the atomic orbitals. So here this is nothing but a psi b I am going to consider. So this position, and here of course we are supposed to have the molecular orbitals, and that corresponds to psi b. And what is that psi b? Psi b is nothing but BMO, which is found by addition of atomic orbitals psi a and psi b, isn't it? And this is nothing but BMO, bonding molecular orbital. And one more we have, and what is that? That is nothing but psi star. And what is psi star? Psi star is nothing but what actually anti-bonding molecular orbital, and how we can write psi a minus psi b, which represents the subtraction of atomic orbitals, and that is considered as the ABMO. So this is how the energy level diagram of a molecular orbital can be drawn using LCAO concept, and these two are nothing but a molecular orbitals. So MO I am going to write here. Atomic orbitals will combine, we get molecular orbitals, that two, one is BMO and one is ABMO. BMO is found by addition, overlapping of atomic orbitals. ABMO is formed by subtraction, overlapping of atomic orbitals. And if you compare the energy, as I represented, energy will be in this fashion. So energy of BMO is less than combining atomic orbitals. So know this concept. I repeat, energy of BMO will be less than combining energies of atomic orbitals, and what I am going to say here is ABM is quite stable. Why? BMO is quite stable. Why BMO is stable? Because the energy of BMO is less when compared to energies of the combining atomic orbitals. What about ABMO? ABMO is quite unstable or less stable, you can say. Why? Because the energy of ABMO is quite high when compared to energy of the combining atomic orbitals, and based on this diagram also I can say what would be the energy and stability of molecular orbitals which are formed by the combination of atomic orbitals. And remember, there will be addition of overlap of atomic orbitals here, and in case of ABMO there will be subtraction overlapping of atomic orbitals. That is the concept of BMO and ABMO, and the same thing can be explained in this fashion also. So now I am going to consider the first molecular orbital which is formed. What is that? BMO. As I told you how to define this bonding molecular orbital. Molecular orbital which is obtained by addition overlap of atomic orbitals. I repeat, molecular orbital which is obtained by addition overlap of two atomic orbitals, that is considered as BMO, and it has less energy and greater stability. And how to define ABMO? Molecular orbital which is obtained by subtraction overlap of two atomic orbitals, and the energy will be more and the stability will be less. So this can be represented, BMO can be represented in this fashion we know, and ABMO can be represented in this fashion we know. So how in case of pictorial representation, how we can represent that? So now I am going to consider one very simple example. Later we will see some different examples of that. This is the one atomic orbital. If you consider the particularly S atomic orbital, because the shape is spherical, and try to know that one. The shape of S will be spherical, and the shape of P will be dumbbell, and D will be double dumbbell, the shape of the atomic orbitals as we know. So this is one atomic orbital, and this is one atomic orbital, and this is the nucleus of that and nucleus of that if you consider, and these two are atomic orbitals of same energy and same symmetry. They are going to overlap, and this is nothing but the region of overlapping. This is the region of overlapping. So when such overlapping takes place, so here when there is a overlapping of atomic orbitals, as I mentioned, two molecular orbital is formed. One is BMO. I am going to talk about BMO, and remember, in BMO there will be addition overlapping of atomic orbitals. I can represent like this. For your reference, above the arrow mark I represented, and after this addition overlap, what we are going to get here is, so this is how actually the molecular orbital we are going to get, and this is the nucleus center of one orbital, and this is one orbital. Imagine this one atomic orbital, this one atomic orbital, they are going to overlap, and you will get a molecular orbital, and there will be addition overlap, and here actually there will be the probability of finding the electron will be more, or I can say this is actually we call it as a molecular orbital, and particularly addition of atomic orbitals takes place. So therefore this is nothing but BMO, bonding molecular orbital. So now we will see the second one, how actually ABMO can be formed. Remember that in ABMO, this is one more kind of molecular orbital, the same kind of atomic orbital I consider. This is the one spherical atomic orbital, one more spherical atomic orbital. They are supposed to overlap. But what kind of overlapping? This is the nucleus, this is the nucleus. But what kind of overlap takes place in case of ABMO? There will be subtraction of atomic orbitals. So psi A minus psi B I am going to consider. And if there will be a subtraction of overlapping of atomic orbitals, the kind of molecular orbital what you get is, this is how I can represent the shape of what actually the molecular orbital, and here this is the nucleus of one orbital and the nucleus of one orbital. So if you consider BMO and ABMO, remember this is the molecular orbital corresponds to BMO, this is molecular orbital which is corresponding to ABMO. So now try to imagine what I am going to say here. So here the electron density will be more, because these atomic orbital are going to overlap in addition fashion. So therefore this is a region where the probability of finding the electron will be more, and that is considered as the BMO. Remember that in a BMO electron density will be high. But how I have drawn this structure and what is the meaning of that? So when there is subtraction kind of overlapping of atomic orbitals, this is how the molecular orbital we get. Of course this is the two nuclei, but here we have have a region. So this is, of course, this is a region, but in this region the probability of finding the electron will be 0, or you can say the probability of finding the electron will be negligible. So there is no presence of electrons in this case. Then where would be the position of electrons? At an instance the electrons will be in this lobe. Sometimes at an instance the electrons will be in this lobe, but the position of electrons will be not exactly in this fashion, in the center, and that is termed as ABMO, and that is considered as node, N-O-D-E. Node is nothing but the region where the probability of finding the electron is 0, that is termed as node. So here in this fashion actually there will be a probability of finding the electron will be negligible. In case of BMO, the probability of finding the electron will be more. So this is how when two atomic orbitals will combine, we get BMO and we get ABMO. BMO by addition fashion, ABMO by subtraction fashion. So electron density will be rich in case of BMO, electron density will be poor or 0 or negligible in case of ABMO. This is how pictorially you can represent the formation of BMO and ABMO. That is how two different molecular orbitals are formed by the combination of atomic orbitals. And we'll see what are some features related to this BMO and ABMO, and we'll see what are the features related to BMO. So what are the main concepts related to BMO? So now the same points I explained we'll write in a systematic manner. What about the energy of BMO? Energy of a BMO will be less when compared to the energy of combining atomic orbitals. So low energy, the energy of a BMO will be very low. And now second one I am going to write, what is that? High electron density. Electron density is very high. Why? In case of BMO, electron density will be high because atomic orbitals are going to overlap in addition fashion. So therefore we get a molecular orbital in the center, in this region. The probability of finding the electron will be more, or I can say the position of electron will be here and the number of electrons will be more, or I can say electron density will be high in the case of BMO, and that I represented here. Now next we will see lobes of same sign. If there is a combination of atomic orbitals of lobes of same sign, so of course here we have yes atomic orbital, we have only one lobe. So if you consider p atomic orbital, this is one lobe and this is one more lobe, and for the identification we can represent a plus and a minus. Remember that when there is combination of atomic orbitals which is of same sign of the lobes, then there will be a formation of ABMO. While explaining how does actually p atomic orbital are going to overlap, we'll use that concept here, but right now you remember when the lobes contain of the same sign, then there will be a formation of BMO. And now we'll see what about the magnitude of a molecular orbital. The magnitude of the molecular orbital of psi AB will be greater when compared to psi A and psi B. You try to know magnitude of molecular orbital AB numerically bigger than psi A and psi B. While pictorial representation, in case of a BMO, we need to draw quite a bigger representation, quite a bigger molecular orbital, because the energy will be less we know, but that is numerically bigger when compared to the magnitude of psi A and psi B I am going to consider. And one more concept I am going to say here. What is that? Of course the electrons will be present, and these electrons contribute to attraction of the nuclei, attraction of two atoms. Of course we have the electrons over here, electron rich we have of course, and these electrons are going to contribute in case of attraction of the atomic orbitals. Remember, if BMO is formed, the electrons they are going to contribute, every electron, each and every electron what is present exactly in the middle, they are going to contribute to the attraction of atomic orbitals, what we consider, and all these are related to the concepts of BMO. And now we'll see what about the concepts to be related to ABMO, and now I can easily explain, since we explained the concept of BMO, what about the energy of ABMO? Energy of ABMO will be high. and because of that reason that is quite unstable when compared to BMO. High electron density in case of BMO. What about electron density in case of ABMO? As I mentioned, the probability of finding the electron in this region is negligible or zero. Okay, so therefore very low electron density you can say, and negligible electron density you can say. Electron density will be very much negligible, or you can say it as 0, and that corresponds to a concept of node. If the lobes of same sign, when they overlap, we get atomic orbitals, bonding molecular orbital. When the lobes of different sign, remember that, when you have two lobes of different sign, and then there will be a formation of antibonding orbital. So here we have a plus and a minus, and if you consider one more p atomic orbital which is of a minus and plus, so we have two different lobes with the different signs. So in this case there will be a formation of ABMO, antibonding molecular orbital. And if you calculate and if you try to know the wave function or the magnitude of a molecular orbital, that is quite smaller when compared to magnitude of atomic orbitals of combining orbitals, whereas every electrons in BMO contributes for the attraction, whereas electrons in ABMO they contribute. Electrons in ABMO they contribute for the process of repulsion in between the atomic orbitals, so that there will be no extent, or you can say the extent of overlapping is very poor in case of what actually ABMO, because every electron which is present in the molecular orbital, particularly ABMO, they contribute to the repulsion of two nuclei or two atoms. So all these are the properties related to BMO and ABMO, and try to know this. You need to remember, if the lobes of same sign we have, BMO is formed, and the lobes of different sign we have, ABMO is formed, and all the properties are very simple, you can remember in a very easy manner. And now we'll see, after knowing how actually molecular orbital is formed, and by knowing the concept of LCAO concept and the energy and the stability, and how actually BMO, ABMO is formed, and what are the key features of that, now we'll see how actually S-S combination of atomic orbitals takes place, and S-P combination of atomic orbitals takes place, and finally P-P combination of atomic orbitals takes place. First we see S-S combination of atomic orbitals to form BMO and ABMO. S-S atomic orbitals combine. So now just see, observe, the shape of S atomic orbital is spherical, and this is S atomic orbital, and one more S atomic orbital is going to combine. For your representation I will write this is S atomic orbital, this is one more S atomic orbital. You can consider 1S or 2S as an example, should be of same energy and same symmetry, and this is the region of overlap as we know. And when the two atomic orbitals overlap, and then we get what actually the molecular orbitals as I mentioned, but that depends whether it undergoes addition overlap or subtraction overlap. If there is addition overlap, that corresponds to BMO, and if there is subtraction overlap, that corresponds to ABMO. First we'll see how BMO is formed, and we'll see how ABMO is formed. And I mentioned one property, that if the lobes of atomic orbitals of the same sign overlap, we get BMO. If the lobes of atomic orbitals of different sign overlap, we get ABMO. So for that I represent, this is one sign plus and this atomic orbital is one sign plus. So the lobes of the same sign we have, and then what happens, there will be a molecular orbital, particularly BMO. So this is how actually the molecular orbital is formed, and here I can mention one sign plus because there will be addition of overlap of atomic orbital, and this is nothing but what actually this is BMO, that is bonding molecular orbital. As we know, according to valence bond theory, when the atomic orbitals overlap, they overlap in two different fashions, isn't it? One is head-on overlapping or coaxial overlapping, you can say, and one more is sideway overlapping. If there is head-on overlapping, that corresponds to formation of sigma bond. If there is sideway overlapping, that corresponds to formation of a pi bond. So here the two atomic orbitals are going to overlap head-on or coaxial, you can say, and here I can represent this is a sigma. Okay, so sigma we are going to get since there is a combination of atomic orbitals in the head-on fashion. So BMO is formed, and I will see how ABMO is formed. As we know, when the atomic orbitals are going to overlap, we get BMO and ABMO. This is 1s atomic orbital, this is 1s atomic orbital. If the lobes are of different sign, one is plus and one is minus, we can consider minus and plus, and in that case we get what actually ABMO we are going to get. As we know, in ABMO the probability of finding the electrons will be negligible. So based on that, I cannot represent in this fashion. So the lobes can be represented in this fashion here, and this lobe is corresponds to plus, that is nothing but this atomic orbital, and this I will write it as minus, which corresponds to this atomic orbital, and here that is nothing but what actually ABMO, anti-bonding molecular orbital. And in this case also there is head-on overlapping of atomic orbitals, therefore I write it as sigma. So to differentiate whether the sigma is BMO and ABMO, and for ABMO I consider what actually sigma star, and sigma star is nothing but what actually anti-bonding molecular orbital. If I mention only sigma, that corresponds to bonding molecular orbital. This is how when s atomic orbitals are going to overlap to get two different molecular orbitals, one is BMO and one is ABMO, and remember the shape of s atomic orbital is spherical. And now we'll see what happens when one s atomic orbital is going to combine with the p atomic orbital, and that I call it as sp kind of overlapping. Sp kind of overlapping, we'll see. And now for this one you need to remember how actually sp kind of overlapping takes place, and for that you need to have the idea of how actually the p atomic orbital looks like. And for your reference I am going to write here, and all these are the 3D structures. So let me draw the px, py and pz for your reference, because this you need to understand better how actually BMO and ABMO is formed. Let us assume this is z and this is x and this will be the y, and similarly this is z and this x and this one will be y, and same I write here z and x and this will be y. As we know, for p we have px and py and pz. So px we have the shape of p atomic orbital is a dumbbell, and that too in the direction of x. Okay, so therefore how this I am going to show, this is how the p atomic orbital can be shown. So py, so this is how it can be shown, dumbbell shape, and pz and in this fashion. But try to know x, y, z are perpendicular to each other. So x axis we have and y axis we have and z axis we have, all these are perpendicular to each other. This is how the p atomic orbitals can be represented in the form of px, py and pz. So if you know this concept, now I can explain how actually the sp overlap of atomic orbitals takes place. So now I am going to consider s. As we know, the shape of s atomic orbital is spherical. Okay, and now px, py, pz, I consider pz atomic orbital. Okay, so this is how actually the pz atomic orbital I considered, and if I mention like this, and you need to imagine this will be the z axis. So this is s and this is p. You can consider any respective the principal quantum number for that, and you get the overlapping of atomic orbital. This is the region of overlap. So here I am going to talk about what actually BMO means. The signs of the lobes should be same. So the sign is positive, okay, and here the sign of this lobe will be positive. As we know, when the lobes of atomic orbitals they have same sign, then there will be a formation of BMO. So same sign we have, and then that corresponds to the formation of BMO. So how I am going to represent that? So this is how I am going to represent what actually the sign of the molecular orbital plus sign they are going to overlap, therefore I consider here plus, and this minus we have, and that is corresponds to this minus, and this is actually what I said, this is BMO, bonding molecular orbital, head-on overlapping, coaxial overlapping, therefore I consider it as what actually sigma here. And if you observe the molecular orbital, the lobes are of different size. As I mentioned, in a BMO the size, or you can say the magnitude of a BMO will be quite bigger when compared to the combining atomic orbitals. Therefore this is how you are supposed to represent that. Try to understand why I have drawn the structure in this fashion. That is about BMO of S and P, sorry, particularly S and PZ. I have not represented that. Try to know this is PZ only, because in PX and PY the kind of overlapping will be different. Now we'll see in case of ABMO what happens here. So now here I consider this is S, and there will be a overlapping of p atomic orbital, and if I consider plus, that should be minus and that should be plus, because when the lobes are of opposite sign, then there is a formation of ABMO. So now how I can represent that? So this is, okay, the arrow mark I can consider, this is S atomic orbital and this is PZ. Try to know how actually PZ is going to be represented. And now in this fashion, the lobe with the plus and the lobe with the minus, that stands for anti-bonding molecular orbital. And one point you remember, in case of BMO, the electrons are going to contribute for the attraction of the atomic orbitals. That's why you get quite bigger, the lobe we can say. Whereas in this case, that that corresponds to repulsion. Therefore how we can represent that? Therefore that is the repulsion, and this is how I can show the diagram of a molecular orbital. This is of a plus, this is of a minus, this is of a plus, and that represents to corresponding the atomic orbitals, and this is ABMO since lobes of different sign, and this will be sigma again because head-on overlapping is going to take place. This is how the S and the PZ atomic orbitals are going to overlap. And now the question arises, what about the PX and PY? We'll see that one. So yes, we have, okay, and the PX, how we represent PX? This is how we represent the PX. For your reference you will write, this is X, P, and this is PX. Now I am going to consider one more, and this is S and PY in the y axis, y direction in this fashion. Just observe here. So this is S, and here what happens here, PY. So if you consider the overlapping of such atomic orbitals, and remember there is no overlapping in this case. So there is no overlapping of S and PX, S and PY. Why? If you observe the direction of the lobes, of course I have not mentioned which is positive and negative, that is not going to matter here. They are of different symmetry I can say. So therefore there is no overlapping of such atomic orbitals. In case of PX, PY and PZ, only PZ is going to overlap with the S atomic orbital, whereas PX and PY are not going to overlap with the S atomic orbital to form the molecular orbital, and there is no overlapping you can say. And these two are considered as non-bonding combination of atomic orbitals. Remember, non-bonding combination of atomic orbitals. Why? Because there is no chance of formation of molecular orbital. Because of that I can say these two are corresponds to non-bonding. For your reference I will write here there is no overlapping, and here there is also no overlapping, and that is corresponds to non-bonding combination of atomic orbital, and this is also non-bonding combination of atomic orbital. That is how actually the sp overlapping takes place. This is the reason why I explained px, py, pz to know better how actually the lobes of a p atomic orbital looks like. Now I am going to move with the next one, that is how actually pp atomic orbitals takes place. pp atomic orbitals, the combination of atomic orbitals to get respective molecular orbital. P atomic orbital, as we know the shapes px, py, pz. So now we'll see how actually the atomic orbitals are going to overlap. This is one p atomic orbital. Let me consider this as pz, and one more p atomic orbital, okay, and this is also pz, and I consider it as minus and plus. This is minus and plus and minus. As we know, when there is lobes of the same sign, there will be formation of BMO. So how BMO is formed? So try to know this will be the formation of BMO, quite a bigger lobe we need to consider. Just see how I am going to draw the structure of that. Yes. So this minus, this is the region, the lobe corresponds to this atomic orbital, and this is the region corresponds to this atomic orbital, plus addition overlap. So this is the region where we have the probability of finding the electron will be more, and this is nothing but BMO, bonding molecular orbital. Since there is head-on overlapping, you can say, therefore I can represent it as sigma. If there is head-on overlapping in case of ABMO, we need to represent it as in the form of star here. So similarly, we represented BMO in the form of sigma here, and ABMO, sorry, you need to consider here it as a star. Okay, that star represent anti-bonding molecular orbital. Now, what happens if the atomic orbitals, the p atomic orbitals, are of different sign? So I consider minus and plus, and here I consider minus and plus. Let us assume, and this is also pz, and this is also pz. And now what happens? There will be a formation of ABMO. As we know, in ABMO there will be a repulsion of the two nuclei because of the very negligible electron density as I represented here, and the lobe of the ABMO will be quite smaller when compared to the atomic orbital. So how we can represent that? So now observe here. This is how the ABMO in that case can be represented. So this is minus and plus, and here it is minus and plus we get, and this is ABMO, and of course there is a head-on overlapping sigma, and since it is ABMO you need to mention star in that case. This is how PP overlapping head-on fashion takes place. Yes, atomic orbital spherical in shape, there is no big deal in that one, but P atomic orbital we have a PZ. Along with we have Px and Py also. In the Py, if you consider Px and Py, how actually the atomic orbital combining takes place, I am going to explain now. So let us assume this is one Px and this is one more Px. Try to imagine this is Px and this is also Px, and I consider of the same sign, plus and minus and minus, plus minus minus. Same sign of the lobes, they are going to overlap. As we know, when there is a overlapping of lobes of the same sign, we get a bonding molecular orbital. So how actually the bonding molecular orbital is formed in this case? So now let me represent that. So this is how the BMO of this p atomic orbital is going to be found, bonding atomic orbital. So here there is a electron density plus and minus which corresponds to the lobe. And now if you observe the Px and Px, they are going to overlap in a sideway fashion, isn't it? In the previous case there will be head-on overlapping. In this case a sideway overlapping, therefore I can mention it as what actually pi. So pi represents there will be a sideway overlapping of the atomic orbitals. So now we'll see what happens if the lobes of different sign will overlap. So plus minus I consider, opposite of that minus and plus, this is Px and this is Px if you consider, and there will be a formation of ABMO. Okay, ABMO, and there will be a very repulsion of the electrons, repulsion of atoms due to the electrons present everywhere, and this will be plus and minus, this will be minus and plus. This is how ABMO can be represented, since there is a sideway overlapping pi, and since it is ABMO I need to consider what actually pi star here. So this is how actually PP overlapping takes place. So this is, I can explain how SS and SP and PP overlapping of atomic orbitals takes place, and P atomic orbital is a dumbbell, and I represented in this fashion. So one thing I want to highlight here, so in some books they used to mention with the sign, that is the plus and minus, that is okay, and in some reference books they used to mention out of these two lobes they used to shade one. Okay, and if they shade one, and to identify and which one is going to be considered, and if you consider one more the atomic orbitals of shaded, and the same shaded lobes we have, and then we have a BMO. If shaded and unshaded part we have, and that is ABMO we can represent. So this is how the atomic orbitals are going to combine to get a molecular orbital. But one thing you try to know, the concept of non-bonding combination of atomic orbitals in case of S and Px and Py. So here I represented Pz, I represented Px. Similarly, the Py also takes place. Okay, so as same as, as I represented this Px, and similarly Py also takes place, that too of sideway overlapping to form pi bond. So this is how, using molecular orbital theory and the concept of linear combination of atomic orbitals, we can explain how actually atomic orbitals will combine to form BMO and ABMO.